All right, this is the day we've been waiting for. Maybe you've not been waiting for it as quite as eagerly as I am, but I love presenting this particular section. And the basic idea, which is shown on the other screen here, involves two characters, Bob and Alice, who are going to take us through some of the thought experiments that are involved with this new approach to both relativity and quantum mechanics. The Bob and Alice thing is something that you'll find in all the literature in quantum electronics and quantum information theory. And basically it just means B and A. Instead of saying a light wave goes from A to B, they say, no, Alice produced the light wave and Bob picked it up. That's very popular now in the literature, so get used to it. We have a few more characters. We have Carla and Donna and a few others that are going to be coming online later on. But basic idea of the cartoon, which is done by my friend Harry as a local lawyer and artist, is that quantum mechanics and relativity are the two pillars of modern physics, but they're the ones that have, I would say, unfinished axioms. And by finishing those axioms, we make it a lot easier, both computationally and also pedagogically. I would point out this book, Mad About Physics, which has this beautiful little passage by D.H. Lawrence. If you're like his poetry, that's one that applies very much to what we're talking about here. My thesis advisor was looking very happy there, talking about the pleasure of finding things out. This has given me a lot of pleasure being able to do it. I wish he was still alive and could see it. The thing that he's supposed to have said is, if you think you understand quantum mechanics, you don't. But as I Google that, I can't find a direct relation. I get about 16,000 pages hits, and I've looked at a few of them, but I haven't been able to find anything. The best I could find is Niels Bohr saying anyone who is not shocked by quantum theory has not understood it. That, I would say that's true, but I don't think that Feynman would put a catch-22 into anything about physics, and that's what that is. So I'm going to pass that one up, but let you know that it's part of the lore, whether it's true or not. Now, what I would like to do today is this whole thing, but it really only starts about halfway. Most of this is whereases and fine points about the history and the philosophy of this. And as you can see, Bob and Alice regard these two subjects, SR and QM, special relativity and quantum mechanics, as foggy and opaque. And I symbolize that on this slide by a picture of the University of Arkansas on a fairly foggy day. And the question is, can we improve the situation? And it isn't just at Arkansas that we have had this problem, it's the whole world. This is a paper from the American Journal of Physics that went through laboriously various quantum mechanics books and came up with 9 separate formulations of quantum mechanics. And each of them, in a sense, axiomatically, shall we say, conflicted with each other. I hope this ends that. At least it's a step in that direction. And in order to do this, we have to take some critical review of, first of all, the originators of these two pillars. First paper, 1900, Max Planck. That's a quantum mechanical study of radiation in a high temperature, low temperature. Special relativity, that's definitely first published in 1905. But they're both about light. They're both about electromagnetic waves. Now, Galilean relativity, that needs some critical review. As I said, that's the thing that's, in a sense, going to fail. But we need to learn how it also doesn't fail. That's what we'll do today. That's right about in here, where we make Galileo happy again. And then this whole idea of this speed of light being so fixed by Ken Evenson, Jan Hall, and there's 3 other authors for that 72 paper. We need to talk about that in some detail, and that's what is happening right here. Where we take on something you've already seen, the keyboard of the gods, that's per space-time, and how it rules space-time. We're going to go over that again, and that's what your homework assignment was to do with. And in fact, your homework assignment was to make a graph that's going to come up at the bottom of this lecture. Now, the one thing that we'd like to get started with, but we won't go very far, it says 3 pages of the idea of quantization, or quantized wave number. Wave number means wave, an integer number, or half integer. That's something we want to mention today. We won't go much beyond just mentioning it. And then the quantization of amplitude, that's called second quantization. We'll be getting to that much later, but we'll mention it also there. And then the whole idea of getting familiar with the light that we're going to play with to make the thought experiments for, well, basically the rest of this course. And we'll do an infrared beam with 300 terahertz. We'll do a nice visible turquoise green, beautiful Caribbean, 600 terahertz. We've already mentioned that. We'll do an ultraviolet 1200 terahertz. And all of these things are available at laser quality now, so this is not outlandish, but it certainly would have been, any of that would have been outlandish in 1900 and 1905. And then the whole idea, and this is, I think, the key to this development, the hidden key is the understanding of modern physics is the Doppler frequency shift. Now, Doppler is talking about sound in 1600s. How can that help us? We need to see that. And then we have Bob and Alice using Doppler to deduce a new kind of axiom that really makes sense. And then they go and they discover something called rapidity, and that turns out to be Galileo's Revenge Part 1, where he gets to save face, so to speak, in a big way. And then there's some other things that involve his revenge Part 2. So let's get started here with this, because the main idea of this is we can clarify and simplify. That would be nice, and I say we can clarify by simplifying it. So that's what we're going to do. This is called using Occam's razor in development of philosophy of this, if there is one. Now, we should once again note that these 2 subjects are very much a story of light. And so we're basically going to make all of our laws of physics just by looking really carefully at a box of light. And the idea is that, first of all, Galilean relativity, as we know it, involving velocity, fails terribly. We have to see how terribly that is. But then it revives, and we'll do that about halfway through the lecture, I hope. And I want to make sense of this speed limit. That's, I would call, a showstopper for modern physics. People just breeze through it, but they shouldn't. And one of the people that didn't was Ken Evenson. He decided he was going to measure it with great accuracy, about 1,000 times better than anybody had, because he had the lasers to do it at the National Institute of Standards and Technology. It was just waiting to be done. So here are the people that were involved in that project in 1972. Now, the Nobel Prize was awarded after he died from ALS. He was very much a bicyclist, and he hit in an accident, and that's probably what caused it. But in any case, he was the first author on the paper that Jen Hall is the late, shall we say, the last author. Okay, now, this speed limit needs to be looked at. So, as I say, here's Albert. And his idea, and this is in his book, The Meaning of Relativity, is that the pulse wave that you get from a lightning flash hitting the railway station at the center of these railroad here, and this is my figure, he doesn't have one that's quite like this because it's extended somewhat. The idea is that no matter what speed you are going on a train, you will, if you're capable of measuring the speed, that's a very difficult job at the time that this was being talked about, you're still going to get this one number, this one speed limit, you see. And that's what I call a pedagogical showstopper. This is something that just is inconceivable. And it's cartoon-like. It really goes back to Chuck Jones's famous cartoons involving the Roadrunner and the Coyote. And the Coyote, if you recall these cartoons, is buying all this very expensive and high-speed equipment from the Acme Corporation. Yeah, everybody knows about this. Okay? So every time he gets something like a rocket-powered pogo stick or a rocket-powered skateboard, he goes faster than he did the last time he tried this stunt. And still, no matter how fast he goes, here comes a Roadrunner. Meep, meep, same speed. He does, isn't as he can't catch a Roadrunner. He can't even begin to catch it. He can't take 1 mile an hour off the speed of the Roadrunner. That's a showstopper. That's not something we are used to. As I said, if I want all of you guys to go 3 miles an hour that way, I walk 3 miles an hour this way, and boy, there you are, all going 3 miles an hour that way. If you're light, I don't change your speed at all. No matter how fast I move, even if I go 0.99999 c, it's same speed. So we got to figure out why that is. What's making that happen? That's really important. That's something light waves do. We just got to get used to it, and then see why we should get used to it. And also, we have to stop using pulse waves, at least for now. So the question is, since when is a cartoon physics reality? Well, this is one case where it is. It is definitely, as we're going to prove, very real. Now, the trouble with a pulse wave is it's really complicated. It's a whole bunch of cosine terms, as we've seen. The more cosine terms, the sharper you get, and so forth. It's very comforting in a sense that it's Newtonian. There's a place for everything and everything in a place. Okay? The PW peaks are very precise in locating where the wave is. But that's not what we want. We want something that will work for us. And that's why I'm picking the CW, the continuous wave axioms that Evanson's lasers used. So what we're going to do is we're going to use Occam's razors and chop out all the high harmonics except for one, the very first one, which is a nice CW, cosine wave, colored wave, or coherent wave, or continuous wave. That's actually the jargon. CW means continuous wave. Okay? So we're going to make an axiom that does make sense. Now, I'm not going to say what it is, just you can read it, but let's wait until we get to Bob analysis showing us why I would want to do this sort of thing. But one of the first things you notice is that what the wave gives us are precise zeros. They locate places where the wave is not. Okay? Idea of looking where something isn't. Something, you know, there's a lot in physics that acts that way. It's a very Zen-like situation that we have sometimes in physics. In any case, instead of having this thing, we're going to have a beautiful blue-green 600 terahertz laser that all of these trains can explore. And what we need to do is show that the phase velocity indeed is the same for all of these trains, but they do see a difference. When this one's going this way, it sees the color get bluer. If he's just standing still, then he sees the proper color for 600 terahertz. If he goes this way, away from it, he sees it shifted to the red. So this lets us actually do experiments where we very precisely tell how fast we're going using the light wave. That's important. And the Doppler shift is what makes that possible. And this is a first order effect. Blue shift. It's going to be written with an exponential about 3/4 of the way through today. Okay? You'll see why that is a really cool thing to do. Okay? So, here is, to my mind, the major objection to the current way of presenting relativity in quantum. It's the only major theoretical development I can think of in all of physics which starts off with second-order effects. And you've heard of those, the Lorentz contraction, the Einstein time dilation. At the speeds we're used to, this is really tiny and really mysterious. We want to clobber that mystery before we're done with a couple of lectures here. I want to take that mystery into the trash can where it deserves to be. Now, we're going to do that by doing first things first. All of the developments that I have in the shelves back there use Doppler shift. It's an afterthought. You get done with the theory of these funny little things, and then you say, oh, by the way, here's the Doppler shift. We're going to do it backwards. Okay. So we're going to start by doing the first things first, look at the Doppler. But before we do that, we must deal with this enigma. What is that speed limit doing? What is it telling us about the universe? Right, as basic as I can make it. Okay, now in order to do that, I must review something we've already talked about, and that is the idea of, well, first of all, space-time. We started the course with some of that. But the per space, per time, we've got a little bit of that so far. I want to review the kappas in the news, the kappas being the wave number. In this case, I'm looking at a wave number of 3/2. Here I'm looking at a frequency, nu, of 4/5. Okay, just using fractions here to show this. And the idea is if you push a button on this plane here, it's like a keyboard, say the keyboard of the gods, a prosaic way to express something that we at first anyway, don't think we have. But anyway, the idea is I push this and I get this frequency, but I also have specified the wavelength. I can go all along here and have the same frequency with different wavelengths. That's something you might say that only the gods could do such a thing. Okay? But the idea is that that button right there causes you to produce a wave that has a certain wavelength, that's the inverse of the wave number, but a certain period that's measured in Hertz's units, Heinrich Hertz's units, okay, which is the inverse of this number here, 5/4. Okay, that's 1 over nu, tau 1 over nu. Just to review that, we've already been through it, but that's fine. And also, while we're at it, remember the Greek letter tau for t, or 1 over nu for the time, okay? And the nu here is a Greek n. Or I use the Greek u for nu. It's like I can't say n. But omicron is what I am using because I don't want something that looks like v. So you'll see omicron here. We just put this in this time. TC finally got a font that really shows. And that's what we do for that. And then 1 over kappa, this guy here, the wave number of waves per meter, this is the number of waves per second, that has an inverse. This one is 3/2 here, this one is 2/3, okay, over there, you see, and of course the Greek L for length of the wave, that's the 1 over kappa, okay. Now the K, I guess, Greek or otherwise, comes from Mr. Kaiser, and Mr. Kaiser is somewhere here. Yes, there he is. And you can see they're about the same time of, of science. This fellow lived a lot longer than this, but they were born in the neighborhood of within 4 years of each other. And both of them have units named after them. Everybody knows Hertz. Very few people, except for some chemists that do spectroscopy, know of the Kaiser, 1 inverse centimeter. But anyway, that's the idea. This is the inverse space of this. We have a better feeling for this one, not so good a feeling for this one at first, unless you're a wave genius of some kind. The idea is you press this button here, and you get that wave over there, and you not only get a little dinky sine curve, but you get something that continues everywhere and for all time. And the basic idea is that the velocity of this is what we need to analyze. We need to understand what it means to have a wave propagating in space and time with a certain velocity, you see. Now, I will pause here to bring this computer over here up to speed so that we can show some of the apps that might be worth playing with for you as you study this stuff. But let me bring this particular app up and see if it's in working order right at this moment here. It's under basic coordinates. If you control click on it, you can make changes of things here. For example, I'll have a unit circle is helpful here. A unit square might be helpful as well. And may as well show the target point icon right there. The rest of these things are adjustments. Two-figure accuracy is fine. So the basic idea is I grab this icon here, and as I raise the frequency, you see the period goes down. The period goes up as I lower the frequency. As I reduce the wave number, the wavelength gets really long. As I increase the wave number, the wavelength reciprocates by getting shorter. Okay, so that's the main thing that I want to show with this that's qualitative, that you have to get used to. Is big things here become little things over there, just the opposite, vice versa. So that is really all I need to say here. Now let's be a little bit more quantitative, which is what that one's really for. And that is that here, distance over time, that's the speed of the wave, is just the wavelength over the period, you see. Okay, divided by the period, that is however many times you go, the wavelength is how big are the feet or the legs of the wave that's doing the traveling. Okay, so I've got everything as fractions here. That's something we try to do with that one too, but it is difficult to do that. So we'll get that working sooner or later. Anyway, as I take the period here and divide it into the wavelength here, you see what I'll get is 2/3 divided by 5/4. Well, that cancels to 8/15. That's the speed of this thing. And the other way to do it, which we need to know just as often, is that the wave speed here, which equals the slope to horizontal as opposed to slope to vertical, this reciprocal, you see, of this. Instead of being lambda over tau, we're going to do nu over kappa. That's per seconds over per meters, which makes meters per second. So that is something you can check yourself on. So this is the key idea to understanding wave velocity. Is this is a control panel, then the wave does whatever the control panel tells for each wave. I press 2, which is what we're doing the homework on right now, is at 2 CW. This is just 1 CW here. Okay? So there are the formulas all stacked up. You can study them on your own. In this case, we've got 8/15 meters per second. Okay? Now, what we need to do is just look for a moment at what wave number gives us later on in quantum mechanics. In quantum mechanics, it's quantized if the wave is confined to some sort of jail or box. In this case, a simple one-dimensional box confines it so that the wave number has to be half integer. That is the smallest wave that I can get. I should say the longest wave that I can get in that box is one that has a half wavelength to there. Now if the box is a circle, I don't get to do half. I got to do one full wave length or 2 or 3. I don't get to play with halves in that situation. But in any case, that is the basic idea, and here's the per space time showing you a wave that has a certain dispersion function, sort of like light, that is a straight line getting bigger and bigger, but in quantum jumps. I can't do anything in between there that satisfies these, what we call boundary conditions. So I'm confined to this, or that, and so forth, ad infinitum. So that's first quantization. Now there's another kind of quantization that's coming up, but notice that this is a quantization of kappa, wave number, a half quantization in this case. Now, the second quantization, which we'll study a little bit later on, that's quantum field theory, is just simply the fact that the oscillators that make these waves are confined. Confined in the phase space that we call the phasor. So they have to be quantized too. I can't just have any old amplitude. I am limited to steps of amplitudes. And that's a quantum field. So when you've got amplitude and phase is all you've got with these waves, and they're both quantized. We're working with what's called a coherent state when we draw pictures of waves, and the quantum in billions, therefore we can play classical physics for a very long time here and not be doing anything wrong. But in any case, there are two things here. K quantization corresponds to the color of the wave. The wavelength determines the color because it's connected to a particular frequency. So I call that quality. Then quantity is how big is the amplitude, okay? Number of photons is what that would be called. This is the number of wavons, or whatever you want to call it, in the cavity. So that's all I'm going to say about the quantum mechanics, just to give you an idea of why the name quanta is there, is really all you need to take at this moment from that. But we're working in a neighborhood where when we get done with all this, we can really do some wonderful things with quantum mechanics. Okay, so now it's time to look at the characters that are going to be in this thought experiment theater that we're embarking on here. First of all, I will be looking at 600 terahertz. That'll be our main character. And then there'll be these guys and these guys that are obtained by Doppler shifting, by going very fast, or by tuning your laser up. There's two ways to make colors change here. That's the thing. But let's remember the key relations. When we talk about the speed of, in this case, light, and it will be shown that this is very fixed. That is, after 1982, in a lot of politics by Ken Evenson and Jan Hall, the plus and minus error that was attached to any number that anybody gave for speed of light was eliminated. It was dropped. And you say, well, what are you doing? Some kind of religion here? You say, you know this is right? Well, we don't care because we need a good definition of the meter. And we've got clocks that can track things to, well, at the time, 12 figures, but now we're 18. So we don't have anywhere near that sort of quantitative measure of distance. So we're using this, and that's what opened us for all the wonderful things that are happening, spectroscopy, gravity waves that just happened recently, but all of the stuff that gave you your cell phone, your global positioning system, all that kind of stuff as a result of this clever move right here. So we could get to work, the engineers could get to work. Now, it's convenient if we're going to have this thing be fixed to basically set it to 1, geometrically speaking. Well, a physicist normally would just divide by c all of these equations here, and we're going to do this, you see, nu over c kappa and lambda over c tau. We're going to have a c in front of the time on the space-time, and we're going to have a c in front of the kappa. That will be the horizontal axis in the per-space-time. Okay, so that's something I want to get straight right away. While you'll always see c in front of the time, and then in our stuff, you're always going to see a c in front of the kappa. That's so that when I draw the thing that has a slope, either relative to the horizon or with respect to the vertical, it will have a slope of 1. That is, we'll cut the square plane in half. Makes it easy to do a light cone reversal, which is my favorite symmetry operation at this point. So let's start with 600 terahertz. Okay, 600 terahertz is right there, and it's going to go with, here, 2 times 10 to the 6th per meter. That means a wave number of 2 million. If you can imagine a meter stick, it's going to have 2 million waves on it if it is near this frequency of 600 terahertz, like this laser, which is a little bit short of that. This is a yellow-green. We're talking about a blue-green. It's right in there. Look at the binding on your textbook to see, get used to the frequencies and wave numbers that we have. And we're going to talk about twice that and half that. Infrared light, which is down off of here somewhere, right about there, is got 1 million waves in that meter distance. Okay? And there is the space-time right there, where we're actually looking at one whole wavelength, which is, for this particular thing, one whole wavelength is a half micron. Okay, the full micron is right here. The half micron is right there. That's a full wavelength, and then a quarter micron is right there. Okay, so I've got those units. Micron is pretty much the unit you'll hear people talking about as you walk up and down the halls of this building. Most of them won't be talking about femtoseconds, but this is 5/6 femtoseconds, this is 5/3 femtoseconds, this is the period right here, 5/3 femtoseconds for 600 terahertz laser light, CW. Okay, that's the green, that's our main character. Okay? And you notice the per time units, the length units, and each of them gives a unit slope in either graph. Okay? Now, there's a whole wave taking off on the space-time graph. That's what we got by pushing this button right there. We made that happen on this keyboard of the gods. All right, let's double that up to 1200 terahertz. 1200 terahertz is really a ferocious frequency. I would be sent to jail if I held a device in here that had 1200 terahertz, because I would be burning your skin and your eyes. A lot of it would get scattered by the atmosphere, so I would probably not be sued too much, but I'm not going to try it. But I'm going to notice that this spectra has gotten half as big. We're now talking about a quarter micron. That's UV. Very hard UV. Not visible, except it would be visible because it would fluoresce your vitreous humor. And it would pretty much blind you in doing so. So don't play with this stuff. It's dangerous. And it makes waves everywhere. Now here's a very nice, we've got all kinds of this just caressing us. This is a case where I've come down from here to half of where I was before, and I've doubled this thing from there, actually 4 times now to get back up to here. This is infrared light. This is what keeps you warm in this neighborhood of the spectrum. Below visible, this is the visible right here. Well below visible, just like that one is well above visible. We are very blind to the universe, in case you don't know it. So there's the 300 terahertz. And here is the waves it makes, just from pushing that button. And then if I push the button on the other side, I get the wave to come at me. And this time it's not dangerous. It just makes me a little warmer. I probably need that. Okay, now, optical Doppler frequency shift. As I say, this is a hidden, it's in the back of these books. It should be in the first page. Understanding modern physics. Okay? What we're going to do is we're going to let Bob and Alice tell us about Evenson's CW axiom, continuous wave axiom. Now, in order to do that, I need to say what the Doppler shift is. And this is just going back to the 1800s. I'm sorry if I said 1600s before, I misspoke. But Christian Doppler, we're talking about sound. But there's, in this qualitative sense, there's no difference. If I have a wave going like this, at some speed, say 700 miles an hour for sound, and I start off at, say, 50 miles an hour, 100 miles an hour, I will hit the waves less often than if I just stood there and waited to be hit by the wave. Here, here, and here. If I run, you see, I'm outrunning the wave, so I get hit later. And that's a first order effect. As soon as the velocity goes here, I get a first order change in the amount of time between hits. Okay? So the idea is that I can move as fast, in the case of light, as approach the speed of light in principle. Okay? I can move fast enough this way so that this green light that's coming from a source way over here, and I'm running away from it, and I'm running away from it faster and faster, I'm looking to see if I can find something special about that light at a certain speed, but what I'm going to find is the way light gets redder and redder and redder and redder, and it's gone. It's gone completely. It has no frequency, it has no amplitude. It turns out amplitude also Doppler shifts because it's a frequency too. Now that sounds really weird, but we'll prove that later on. Okay, so the light dies. I can run after it. Oh, it's gone. It's gone. Where'd it go? Let's try going the other way. If you go the other way, instead of going hit, hit, I go hit, 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 hit. I'm running into them sooner. Just imagine that's water. You're in a boat. You go with the way. It's a very long time before you pass over. You go that way, the other way. Bam, bam, bam. Right? And that's what's going on here. That's a blue shift. Okay? And you can go towards the speed of light on this direction looking for something special about that light. But this time, instead of light dying, you die. Pretty soon you're up there in the particle accelerator energy and you're just vaporized. Okay? So that's what we're talking about here when we talk about Doppler shift. Full range, plus C to minus C, almost. And see all the colors it can possibly be. And I mean all frequencies it can possibly be, not just the colors. Okay? So that's what we're after here. Now, we got to see why it is the speed is such a well, just boring. It's boring. It doesn't want to do anything else. We've got to see what the deal is here. So we're going to clarify Evenson's CW axiom. The idea all colors go C. I mean, we're giving the answer out a little first, a little undramatic here, but it's such an important thing that the more I say it, the more I hope it'll stick. But anyway, Alice is going to try to fool Bob. Okay? Bob wears funny earrings and stuff, so he's easily fooled. The idea is that she's shining a 600 terahertz laser, I'm sorry, a 300 terahertz laser, but she is moving really fast. Okay? Bob's unaware she's moving really fast. Now, we realize they're millions of kilometers apart, and lasers travel long distances, so this is not out of the range of possibility. So the idea is Bob's down here, and he has to talk over a cell phone in order to find out what's going on. And Alice says, after Bob says, my frequency meter reads 600 terahertz for your laser beam. She doesn't tell him, I don't have a 600 terahertz laser, I've got a 300 terahertz laser. Now the cartoons that we're going to be showing of this, if I want to show that something's moving relative to the screen, I cartoon it so that it's leaning forward. And just to make emphasis, I draw little speed lines, sort of exhaust lines, to indicate that. Okay, I want to make sure that that's clear. I went through a whole lecture downstairs, and finally somebody raised their hand. One of the professors said, "What are those lines?" So, yeah, let's make sure you ask the question that would make it clear for everyone. Anyway, Alice says, "Okay, so 600 terahertz, what you got?" Well, I'm going to fool him. What is your wavelength? Okay, he's got something to measure frequency. It's a very different measurement from measuring space. He's got something much easier to do, that's time. But you can also make wave meters that are pretty accurate to measure a wavelength. Okay? So, first question. Can Bob tell that this is a phony 600 terahertz? In other words, this thing wasn't born 600 terahertz. It was created by a 300 terahertz infrared laser. It's a cheap version of maybe 600 terahertz. Or is it? You see, that's the question. Okay? Question 2. If so, and this is Alice's leading question, what phony lambda does Bob see? Okay? Now we already know what the wavelength of 600 terahertz is. If you remembered, we're going through this. That's a half a micron. But this is phony green, maybe, right? Might be something else. So this is a good question. This is a good leading question for this whole course, this whole approach. Okay? So we go to per space-time to answer it. And we say, okay, what Bob is seeing is 600 terahertz. Somewhere on this line here, all of which these points have 600 terahertz in per time frequency. Okay? They all have 6 trillion hertz. Okay? But the question is, could it be here? Could it be here? Could it be here? Could it be there? Could it be a C, A, B, C, D? What is it, you see? Could it be a light whose slope is pretty darn fast, okay, very high? Or could it be something like that one right there, or maybe even down here, it's pretty slow, okay? That's the question, you know. Well, where is this phony green, you see? Well, to make things happen faster here, the answer is C. The one with the same slope as all light has. If he sees green, then he measures half a micron. 2 million waves per meter. The vacuum, it turns out, was constructed by a lowest bidder. And the cheapest thing is to have only one dispersion relation, which has no dispersion at all. That's the real rub here. So if you were to find that his phony light was here, going faster than light, then why not here? And then here. Or maybe slower as well, you see. It's like David Hume's argument against miracles. He says, if you got one miracle, then you can have 2 miracles. And if you got 2, you can have 4 miracles. And pretty soon, you're up to your fetlocks in miracles. We can't afford to have a vacuum that expensive. The vacuum just can't find any way to make a mode that's green of anything but that particular wavelength. And that means if it's a red light, it's going to be down here. That's the one we're having. Only one kind of red allowed, one that goes C. Only one kind of green, only one kind of every color, and then I mean every frequency outside of our color range, has the same speed. Now, to go further on this, the answer to the first question is no. CW light carries no birth certificate. Similar to Ted Cruz, I guess, or Obama, or you know the political situation for birthers, right? Here it's true. The light is, you cannot tell anything about where that light was produced. And you can change the frequency by going toward it, and it'll go up, or run away from it, and it'll go down. It's the same damn light. Okay? So, vacuum makes only one kind of lambda for each nu. All colors go C. All colors march in lockstep at that particular speed that Ken Evenson has measured so kindly for us. Okay? Now, that's a logical argument. Here's evidence supporting Evenson's axiom. If bluer waves were even, say, 0.1%, or 0.000% even, slower than redder ones, then each flash from a 5 billion light-year distant galaxy shows up dispersed over 5 million years. What kind of astronomy would that be? You'd see the explosion when it was early, that would be blue, and then later on, the red part, it's all over the place, that's red. You can't make any sense out of that. You would have no astronomy. We just have beautiful psychedelic rainbows in the sky. Blurs, you see. So we really need Evenson's axiom just to make astronomy happen. Okay. Well, what we're going to do now is we're going to let Bob, Alice, and a third character, Carla, discover a parameter, the logarithm of the Doppler shift. This is as a name that I think is very appropriate. It's called rapidity. It's means how rapid is the a coyote or the road runner, you see. We're going to have something that we can quantify really high speeds very conveniently with. And that begins here. So the notation that I'm going to use, and this is all described just in the first few pages of the Unit 3 that I've given you today. When I do a frequency ratio between a receiver and a source, receivers being those people, and here's the source, it's Alice's laser gauntlet here that she's applying to her various friends who are going in various speeds and directions. As you can see, Bob here is zipping like mad, so fast that he's got a Doppler shift of a factor of 2. Now that corresponds to some pretty high speed, which we're going to be calculating soon enough here. Carla here is not quite as fast, and she's going the other way, as you can see by the speed line. She's headed that way. And she has a reading here that's pretty low, whereas Bob has a very highly blue shifted reading, and she has a, well, I would say equally highly red shifted reading. Okay? And here is 600 terahertz source that Alice is operating. Okay? Now I'm going to use a notation of Dirac brackets that is, I don't see it anywhere. So be aware, this is a new thing, but it's something that we have to get started because what we're really doing is Lorentzian group theory here with all this light. It's very important to, I think, get a convenient notation. So the way to look at this thing is R over S. Imagine that the little thing that separates it is a fraction line. Okay, that means receiver over source when I write it this way. Okay, so Bob-Alice Doppler ratio, that's B over A, that's really nu B over nu A, that's 1200 over the source 600 is 2 to 1. And then Carl Alice, same thing, okay, except now it's Carla over Alice. Alice is still 600, but she's down in the 400s, so she's got 2/3 for this Doppler ratio. Okay? Now, an important point here is Evenson says blue, green, red all march in lockstep. So, show tracks of beams of different colors, fine. The redder colors will have long distances between them that are much bigger than the distances between, say, green light. Okay? And as I try different Doppler shifts, you see, all of these lines are going to intersect these things with the same ratio for each of the dark lines. If I'm going quarter C, I see something like that, you see. So I see an elongation of the green that's the same factor as the elongation that I would see for the red or the blue or any other thing that is marching in lockstep. So that's simple geometry of a pencil of lines having the same ratio. Remember when we used that for superpoles. Okay? So that's the key thing. Same geometric proportion. And that's why we use multiplication to describe a Doppler shift rather than adding. And that's what you find in all these textbooks. They'll add delta to the frequency and call that the Doppler shift. Terrible. Okay? It doesn't work what we're going to do here. So if Alice sends a 600 terahertz and Bob sees 1200 terahertz because of a ratio of 2, okay, it's just B A times her A, all right? But if she pulls up a cell phone that's a 60 terahertz, that'd be a pretty fast cell phone, but or 6 hertz, if she calls up one of the really old-fashioned ones, okay, whatever it is, it's just going to be multiplied by the same number. You see, you use the same number for all of the different frequencies. No matter what the frequencies is, this number is the key thing. Okay, so it's 2 for any of those frequencies, any of the possible things that would be coming his way. All right, that's an important point. I want to make sure that that's seen. That's the geometry that makes this possible. These are all geometric effects. All right. Now, geometric phenomena tend to involve logarithms and exponentials. So it makes sense to take the logarithm of this thing, because this is going to get real big. Okay, so logarithm, you get a number we can work with easily. But one thing we don't want to work with is what everyone seems to be working with, and that's called the relativity parameter, which is the velocity divided by c. Okay, so a 1 TeV proton in the Hadron Collider has a u over c of 0.999995598. Okay, to the precision that's far beyond what they deal with in their experiments. Okay, but still, it's what I call a real pain in the ass. I'll just say it. Okay, this is not what I want to do arithmetic with. All right, so let's take the ratio of source to a receiver. Okay, R over S for this thing. Okay, well, it turns out that that's 2,131. That's cool. But the logarithm of that is only 7.6646. And I can write off more figures, but you can see that's really convenient to deal with. Okay, small, even for huge things. I mean, it makes a Hadron Collider. What they do, they spend billions and billions of dollars and they only got 7.6. Well, now they're up to 7.7 and 7.8. But, gee, we can do better than that somewhere in other galaxies, right? Anyway, we can handle some really high-speed stuff. Now, for low velocities, the rapidity number is u over c, very accurately. Only when you get about quarter c do you start to see some deviation from, 1/4. So the relativity parameter is this if you're not going really fast. If you just do the kind of experience they do around here, well, no problem. Okay? But what we need to do is take a look at how we use this thing. That's what really makes this powerful. So let's take a look at the rapidities of these two cases here. We have 2/3 there, we have 2 here, okay? What is the logarithm based e? Now that's the thing, is you calculate, you got one button to figure this thing out. If you use the old formulas for Doppler, you got to go do about probably 10 or 12 punches on the calculator before you get this number, okay? So that's a convenience right there. Now the log of 2, we mentioned that's 0.69. How many people remembered that? Anybody? No, you should. I have to admit that I sometimes forget, but it's got a mnemonic. Anyway, Carl Ellis's rapidity is actually negative. Okay, now, mnemonic. You can think of the rapidity as Greek R for Greek Romance. Okay? It's positive on approach. Okay? Oh, you're coming to me. Very positive. And then, on reproach, that is, you're going away. Oh no, don't come back. Oh, that's negative. Okay? So, that, that's very anthropomorphic. Okay? And it brings up a question. Why do the stars hate us? They're all redshifted. They all have negative rapidities. Well, if they're watching television and look at our political thing, I can see why they certainly, if I had the power, I would get the hell out of here too. Okay? Well, anyway, those are all things that I want you to help you. You get a feeling for this thing. Now, as far as the negative sign, all that happened here, if I go rho b over a is this, then rho a over b, that's when Bob would be the source and Alice would be the receiver, this is going to be negative, because that would correspond to a logarithm of 1/2, minus 0.69 instead of plus 0.69. And Carla's rapidity is negative, because she's headed away from Alice. Okay? Now, the time reversal symmetry is a key axiom. There are really 2 axioms that we need, and that's Evenson's axiom and time reversal. And time reversal, I think I have time here just to show this. This is back in the old Pirelli site. let's see if it works here. It basically says if I reverse time, which means I take a source and convert it to a receiver, I take a source that's moving that way, I turn it around and make it go exactly backwards. And then this receiver here is going to become a source. Okay? So the idea is that when you do that, and okay, that's kind of what I expected.
You can replace PHP with HTML. There's 2 PHPs and it'll run.
I think we'll pass at this point. Yeah, we'll pass on that. Yeah. So. Yeah. Anyway, it just shows the thing maintaining the colors, and that. Let me get back here to the original. The idea is that if I time reverse a situation where Alice is sending 600 terahertz to you, say Bob, and then we play the whole thing backwards so that she becomes a receiver of Bob backing up, then the ratio just reversed, you see, in this expression, and that gives you a minus sign, and that's really all I need to say about time reversal. This here and that there are time reverse situations. Okay, well, this situation is a little more complicated. Alice says, Bob, Carla, read off your Doppler shift ratios to my 600 terahertz beam. Okay, and also give me your rapidity. Well, they've already done that. Okay, here's rho BA right here. Okay, and relative to Alice, Alice is the source. You see the letter on the right-hand side, and then Carla's come up here with a minus 0.41. Okay, and here is Bob reading off the 0.69, and she reading off her minus 0.41. Okay, minus 2/3 is her ratio, but the logarithm of that is minus 0.41. Okay, so what we're going to do is notice that Carla can answer the question, what is your rapidity, that's rho CB, with respect to Bob? If Bob was the source, okay, what is your rho CB? Okay, there's CB. That's new Carla over new Bob as a source. And I can just go and put Alice into that, you see, multiply and divide by Alice's frequency. And then I have that the CA times AB is equal to CB. That's a little group theoretical multiplication a formula right there. And what's better is that if these things are all exponentiated, you see, in other words, if I look at the logarithm of that thing, that is e to the rho CB, then I get the product of e to the rho CA rho AB. And that is really cool. That is really cool because that implies that all I have to do is take the rho AB. Now that's not rho BA, I need rho BA, okay, which is minus 0.69, and add it to Carla's rho, and I get the rho of Carla relative to Bob. That is cool. And this will work, you see, at all speeds, not just things that are real tiny. This is really neat. Okay? And you see what this is. This is Galileo's number 1. Rapidity as just like Galilean velocity and works for all speeds, right up to infinity, whatever you name. Okay? Things faster than light, slower than light, they all work. This is really cool. Okay? Now, I looked all over the internet trying to find a picture of Galileo that he didn't look worried in. And the one I showed you first is him looking worried at relativity. He somehow saw it in the distant future. He's happy now. That's Galileo's addition. It works. Really cool. Okay? All right, we've got a couple more things to do here, and these are things that we're going to do over again on Thursday, pretty much. But I want you to see them because they're part of the homework. Part of the homework is to take a very complicated 2CW. This is a simple one where the frequencies are the same, but I want you to, first of all, we already know what the answer to this is, that this particular combination of CWs gives me a nice space-time graph of 0 grids, the white, okay? So Bob's impressed anyway. Cool, you guys made me a space-time graph out of real zeros. How'd you do that, you say? And we've got web visualizations and things show that. I'll wait until we're further along here. And Carla says, it's easy to do that. You just get zeros from a wave sum by factoring it into phase and group parts. And that's essentially what you're doing at homework on right now. But for a more complicated case than this. Okay? It's a half sum and half difference trick. Okay? I go half sum and then I go half difference. You see. So what I end up here with is a phasor sum, okay, that includes in the angles, the actual phasor angles, half sum, that's the average of the two different frequency phasors, okay, and then right here is half difference. So that's a geometrical way to see this, just by adding these two clocks of equal, in this case, equal radius. That's the idea here is I have the same amplitudes here, amplitude basically of 1 for these waves, okay? Now this is Galileo's revenge part 2, and that is phase angular velocity adds just like Galilean velocity. And here's where I play that game where I pretend one of these phasors isn't moving. In other words, I get up to the speed of that phasor in a little merry-go-round in this gauge space, and then I watch to see what happens to the other phasor as it goes around. Now, this I can do very quickly on the old machine. I'm going to go ahead and use the old machine, and by the way, this is probably the easiest way to show half sum and half difference. Just take two combs and put them on top of each other. They usually won't be exact, if they're not made by the same manufacturer, it'll always be something different, like 57 teeth versus 60 teeth. And then you'll see that the difference in those numbers is the number of lumps that you see in there. And it's actually half sum and half difference. It makes half lumped counting. Now that's the problem you see with waves, they go up and down. But in any case, put that aside for the moment. You see it says half beats there, full beats, you have to take the 1/2. That's the thing I'm asking you to do on your homework. Here's the half sum and half difference that we talked about, and here's an actual movie of them in action. So first look at this movie right here. This is this guy plus this guy gives this guy, okay? When they line up, like right now, you got a big sum. When they don't line up, anti-align, like there was a line up again, like right there, you get nothing. But you can see what's happening if I just look at the red phasor and watch the green phasor go around its nose, you see. It makes a Thales geometry, which we're going to see. That's the major geometry of quantum mechanics right there. And then I could get on the green phasor too. Now the red one's the slow one, so it's going to be going backwards. Same thing, you see. There's a right angle subtended by the diameter that's making that geometry, and that's what we're talking about right here. Okay, let's go back and I'm going to go forward here. Now this one right here is just a picture that's on the modern, the one that's on the website. This is Relativity's main screen showing. But what I'd like you to see in action here, and I think I could just start it right here and not have a problem. But I'd like you to see this is a case where the baseball diamonds are formed in space-time. This is what PWs do, pulse waves. So here's a pulse train going this way and another pulse train going that way. There are their tracks. If you want to take those waves above the origin a little bit, like I just make this first component here, the 0th component, right on the thing there, then I have zeros pretty much in between where these pulses go, meet each other, have a little dance, and then it kind of looks like a swingers couple's having a tango or something. But the main thing is that you have a baseball diamond, home plate, first base, second base, third base, in space-time, instead of in per space-time, which is what we started with. Now what we're going to do is we're going to Doppler shift over in per space-time. We're going to make this one longer by a factor of 2 and this one shorter by a factor of 2. And when you do that with pulses, I'll show you that in a minute here. Let me just pause this one out and go ahead on the computer here to the next frame here, which is right here. Okay, so what I want to look at is half-sum, half-difference here, where, and this time Alice and Carla are moving relative to Bob. They still have their 600 terahertz lasers trained on him, but they're not going to be making anything like the simple square graph grid paper that you saw before. In fact, this is fast enough to Doppler shift the 600 to 1200, the blue side, that's coming toward Bob, and Bob is seeing that one receding, so he's effectively running away from that one, gets red shifted by the same ratio. Okay? Blue shifted by 2 gets 1200, red shifted by 2 gets 300 for the 600 terahertz in each of these pieces of hardware that the women are operating on the thing. So I get a wavelength here, 1 micron, that's 1,000,000 per meter, a wave number. Here I get 1/4 of a million per meter on this side. That's UV, that's infrared, right? Okay, so Bob says, wow, I gotta wear some sunglasses so I'm gonna look at that thing. And the vector is fierce. This is the, you remember in your homework I asked you to do something that was at 4, and then here's something at 1, right? 45 degrees, okay? And this is what you should get. We are done with relativity. That's the whole story right there. That's what we got to talk about next time. We got to explain what length contraction means. It came from here down to there. What time dilation, say from here, it used to just be up. Now it's up this high. And then there's a whole bunch of other things that they don't talk about, because they're just copying Einstein. They don't put anything creative into it for 100 years. That's what we need to get here, you see. So, basic idea is that thing right there gives you this very nicely, and the pulse wave. This is something I want you to look for in your homework, just for extra credit. See if you can find these guys. Okay. Now, again, it helps to bring this up so that the baseline of the pulse is right, and you have to do just the angle as well as the amplitude. That ought to do it right there. Okay, so now I have pretty much 0 in between. There's one fat old pulse going this way. Everything's going C. This is the baseball diamond warped. Okay? If this is home plate right here, it's a marathon to first base, a short steal to second base, a marathon back to third base, which is off screen here, and then a short steal home. But you should see if you can find those lines on your homework. They're there. The right and the left vectors, wave vectors. And it's half sum and half difference. That's all we're going to be talking about for the rest of this course. All the mechanics, quantum mechanics comes out of this. And that's cool.